Hello and welcome to Allies in Innovation. You know, NASA, they write that you have 5 things you need more than anything when you enter space. You need a system to live and breathe, if you of course send humans up there. You need propulsion power. You need the ability to hold off heat. We mentioned that in the last episode on space here on the podcast. And you need radiation protection. That was also mentioned on last episode. And then you need constant communication, because if you don't have communication, you kind of lose navigation and you lose the satellite or the mission altogether. So that last one is the focus of today's episode. And luckily for me, once again, I have Andreas Stren in the virtual studio with me. Welcome back to you, Andreas.
Nice to be here again.
And again, you're still the lecturer of Aerospace and Engineering program at the University of Applied Sciences in Wiener, Neustadt. And with us also, we have Alexander Spaniol, who is the radio frequency engineer at Terma. Welcome to you.
Hello, thank you.
I think since the topic here is software-defined radio, because that's what we're talking about today, the communication between Earth and the whatever mission that we have out there, if it's a satellite or if it's someone on Mars, software-defined radio, for me and for the listeners outside the deep space industry, what is a software-defined radio or SDR?
So software-defined radios are used to communicate with the satellite and our ground stations. So from the ground station to the satellite, and of course also from the satellite to the ground station. And what is the special point about software-defined radio? In the past, we most of the time had hardware-defined radios, and nowadays we're using software-defined radios. But what does that mean? Software-defined radio is a kind of a radio communication system where we have components that traditionally relied on hardware, for example, modulators and demodulators, signal processors, frequency mixers, uplink or up converters, down converters, and so on. They were implemented in hardware, and nowadays we do that in software. And this combination of reconfigurable hardware with this powerful software makes this radio a software-defined radio. So we try to get as much as possible into software to get all the benefits from there and try to rely as less as possible on the actual hardware itself.
And what does this, I know we touched on this in the last episode with you guys as well, but what does this actually mean to the hardware? Because you say that you needed modulators and you need frequency, I don't know all the words, all the equipment.
Yeah.
But don't you still need that?
Of course you need it, but the thing is that the hardware itself, you don't longer need it, because what you're actually doing, you're receiving the signal. Most of the times you then have a hardware or a component that attenuates your signal, so let's say it makes it stronger, and then you directly digitize it. So you have your analog to digital converter, so you make this analog waveform and digital signal just by making samples out of it, and then you have it in software, and everything else is then done in software, and that's what we do in software. Therefore, we do not longer need any hardware. For example, modulation, demodulation, frequency mixing, so up conversion, down conversion, and so on. That is no longer needed to have that as a physical component.
So now you just basically need a really powerful antenna that can receive all kinds of communication. And
Yes.
what sorts of communication are we talking? Is it just the fact that it can do, my FM radio can do multiple frequencies? Is that what we're talking, or?
Yes, more or less it is exactly that we are talking to. We have a radio frequency front end. Of course, this radio frequency front end, you cannot have one antenna that receives, let's say, 10 megahertz frequencies and up to 6 or 10 gigahertz. That's not possible. That, of course, needs to be suitable for your frequency range. But when you have that, your antenna where you receive the signal, then you are already more or less fine to go with software-defined radio by digitizing it.
Also, advantage would be that, for example, two different antennas can be handled by the same software-defined radio. Whereas in the past you needed two full systems. So you can integrate many antennas into one software-defined radio, for example, and so just switch them. Yeah.
Okay, so I can see. Okay, fair enough. You don't need all the hardware equipment on board the satellite, on board the rover, or whatever you're talking to. You don't need the hardware. But other than the space-saving exercise, why is this a good way? Why is it a good approach?
We touched it a little bit in the last episode. The environmental impacts are always driving the requirement for missions that are out of the atmosphere. So if we have less parts that we need to take with us, there is less risk any part is failing. So,
and the environment here, we're talking. Actually, like the NASA bullets. So we have you need to be able to hold off heat, and you need to be radiation resistant, and all this. So that's the environment considerations that you're thinking.
And hardware parts that are essential or were essential, I would say, always needed own testing procedure and needed to survive for sometimes decades. And the software-defined radio using lesser parts also have lesser risk of failing.
I think of that question there, what you should also answer is the other thing about disadvantages of bringing software-defined radio here into in our case, space industry, into the communication with the satellite is that we, for example, have the big advantage of the flexibility and the reconfigurability of the software-defined radios. Why? We already have talked about that we are going to replace hardware components in order to do that in software. And the big difference between a hardware physical component and the software is that we can update, we can rewrite, we can debug and so on the software. And we can also do that, for example, when the satellite is up in the orbit, because for hardware to exchange it, we would need a human there to do that, and that's more or less not possible. But with software, we can do that. So we can change, for example, our frequency. Here, software-defined radio, Andreas already mentioned it, we have the possibility of receiving several frequencies because we have such a broad bandwidth that we can receive with such an SDR, and we can also receive two signals at the same time and process it if we want to do that. Yeah, modulators, demodulators. In the past, when we talk about hardware-defined radio architectures, they were designed for a specific data rate, for a specific frequency, and a specific modulation scheme. With software-defined radio, you can change that like you want to.
But why would you want to change it?
Why you want to change it? There can be several reasons for that. For example, if you have a satellite mission, you always have a goal. And it may be possible that you, for example, start with low Earth orbit, then you increase your orbit, you get more far away, for example, for the Earth, and the requirements on the communication link, they change. You, for example, need to transmit telemetry, or you need the telecom, also you have your telecommand or your telemetry of the satellite, and this link between satellite and Earth and the requirements of it, they can change, of course, with the orbit. So you may need to change your data rate. You may shift your frequency because you have disturbances here down on Earth, and that frequency you decided to have your downlink or uplink of the satellite. And with software-defined radio, you can shift it. Modulation. There are several different modulation schemes. With software-defined radio, you can change them as you want to, and different modulation schemes have different advantages and disadvantages. But there you always have to deep dive into your specific application, what suits the best for you.
And Andreas, I know there are some risks. There must be some risks also connected to having a software-defined system at all. Can you maybe talk a little bit about that?
Yes, as you already mentioned, the NASA bullet points for the environmental impacts or requirements, I would say, is that raising the amount of software and reducing the amount of hardware parts. We talked about the advantages. The disadvantages would be like that digital systems react differently to radiation than hardware systems do. So to compensate for that would be building redundant systems where two SDRs are, for example, next to each other, or maybe three, depending on your designing process, and you can always rely on that at least one of them works. And the impact of radiation comes in two forms. There's one that is called the total ionizing dose. That's something commonly known like rats or measuring with a Geiger counter or something like that. But there is something most people don't know about radiation. There's high energy particles all around in space. Space is not empty. Yeah. And if these high energetic particles hit, for example, a computer chip, they can induce a so-called single event effect that makes a 1 to a 0, or the other way around. And then your program needs to handle that. Yeah, so that this would be.
So it's basically easier for that particle to, I'm going to say, push the digital system from, well, digital is always 1 or 0, right? So push that 1 over.
And yes,
like a domino.
and that's, for example, a new requirement that came up with SDRs, that these single event effects don't disturb the operation. Yeah.
And what about, does it also pose flanks? I'm thinking like cybersecurity wise. We just had an interview on cybersecurity, and of course, at least for Terma and obviously all defense and space, all that interconnection there is there. Cyber is a very important topic. So what kind of requirements does it set to you and as a software defined or a software specialist?
Yeah, so security is one of the biggest topics because Terma, we are here to secure people by our technology that we make, and cybersecurity, especially for the software-defined architectures, and now in this talk, especially for software-defined radio, is of course a big topic.
Is it something you can build in? Can you design your software so that it's unhackable?
Yeah, it's something that you can't build in. You have to build it in because you need this security. Everything is within software, and when someone, let's say, hacks into your system, then we will have a big problem because they can, let's easily speaking, hijack your satellite. So cybersecurity things like using authentication, encryption, and so on. That is something that we always implement in all our systems at Terma. But for sure, also in software-defined radio and our modems. And
also, as already mentioned, if, for example, if we hope not, a security layer fails, it is interchangeable by uploading a new version.
Yes, you can update your firewall basically. Yeah. Okay. You mentioned in the last episode virtualization, and I think we just touched a little bit upon it in the last episode, but I think it would be good to kind of revisit that. How are software-defined radio and virtualization? How is that connected? And can you maybe just again say a little bit about what virtualization is, Alexander?
Virtualization. That's a hot topic, or quite a topic, and especially also for us at Terma. Virtualization basically means that when you have something, for example, let's look at the software-defined radio. You have a signal, and what we actually do with the software-defined radio, we bring it from this analog domain into our digital domain. So we have it digitally available, and by having it digitally available and making, let's say, virtualization. So, for example, bring it up in the cloud, then we are able to use that from different locations. Where I can bring up here 2 examples. We can talk about, for example, software-defined radio as part of our radio frequency special checkout equipment. And as we know, when we have a spacecraft, it is for sure tested before it's launched. And within this manufacturing, assembly, integration, and testing circuit, we have the testing of our communication module. And by, for example, in this equipment, having software-defined radio, we are able to have all these hardware components that are within such systems, like, for example, spectrum analyzers. We have power sensors. We have signal generators. We have up and down converters. All really expensive hardware components in such test systems. And by bringing software-defined radio in such a system, we are able to do most of these things in software.
So you don't need that expensive hardware at all?
You don't need this expensive hardware at all, because you're already in the digital domain and we can further process your signal in the digital domain.
Yeah, so you have like a digital twin of that.
Yeah, exactly that. Especially when you're speaking then about the operational things. But in testing here, you are then able, with this virtualization, that you provide then this to your customers. So you may, for example, no longer be required to have this big rack directly at the customer. You can have it placed, for example, one rack in the laboratory, let's say in our case, for example, at Terma. And by virtualizing and having this interface or have it hosted in the cloud, customers can book it and use it because it's already digitized and you have it in the cloud. And nowadays, the tech, the network that is required, the speeds, the latency, it's there and it is possible.
It sounds like a huge cost saver.
Yes, it is.
Yeah. What does that mean for you, Andreas? When you said at the university, what does that mean? This is a completely different way of working.
It is a completely other way of working, but it has the same impact. For example, we had an educational satellite named Pegasus. It was launched 2017 and re-entered not long ago. It was in orbit 6 years. It was a big achievement for us. But the thing is, it was a hardware-defined radio on there. And our equipment was built up only for this specific mission. And at the end of the mission, actually the whole setup of the ground station equipment was obsolete. And together with we are planning a new mission called Climb that raises also complexity because we want to change our orbit. That is for I would say for a university and educational task pretty hard. We're working on that, but we already changed our ground station to a software-defined radio system. And what we can do here, not only that it's more cost efficient, we can change the communication parameters, as Alex mentioned. For example, modulation of frequency. We can change it and, for example, listen to other educational satellites from other universities around the world, and we can also incorporate it in our courses to show the students, hey, that's how you communicate with this satellite, and for example, let's change the parameters, and this is how you talk to this satellite. And this versatility gives also the students more insight on the differences and how it actually works.
I think, to be fair, yesterday when I was researching for this interview, I looked up the communication, the notion of communicating with a satellite. So I looked up in the new and fashionable way of looking things up. So I asked ChatGPT basically, what sorts of communication are we talking about? Is it, and quote unquote, is it a walkie-talkie communication where you call it up like you see in movies, right? You see Armageddon. Oh, I'm old now, right? When it's referred to Armageddon as the one. Like any movie on space, it's always like a walkie-talkie kind of conversation. You have someone talking one and the other. What kind of communication? Because a CubeSat obviously is unmanned. Like,
well, yeah,
99% of all satellites are unmanned, right? So, but what kind of communication? What does it actually look like? Is it text? Is it someone writing and then there comes text return, or is it coding, or what is it?
May I take this one? So you always need to think about what information you want to transmit. Okay, if you talk about walkie-talkies, you're talking about an analog signal, a recording of your voice, that needs to imprint it on a carrier wave. And the carrier is like the frequency where everything happens, and then you overlay information onto that. That's when Alex and me are talking about modulation. That's how to pack information on there. And as going for digital communication, we're talking, as soon as we're talking digital, we're talking about binary information. And this information can be imprinted on a carrier in very different ways, and very varying ways of complexity, or let's say information density. Okay. And you need to think about, for example, if you use your car key to open up, that's also part of a digital signal imprinted on your key that communicates with the car. So it's basically everywhere.
Funny note maybe about that, your whole satellite, this hardware-defined satellite, actually used such a modern chip, which is actually used in this to open up the car. For example,
well, we couldn't.
Oh, really?
And what they did at the university is they put it on a platine, 10 by 10 centimeter, twice to be redundant, and that was, let's say, more or less.
I could say we couldn't afford much more, but yeah, it worked.
Yeah, so that's just a funny side note on that. What I maybe also would like to mention here is you were also asking about if it is like a walkie-talkie communication. So one is speaking, the other one is listening, and then he answers. Of course, it's possible. For example, the Pegasus satellite from the university, when I remember correctly, that was on half duplex communication. We're speaking about half duplex when we are either transmitting or receiving. So that was some kind of walkie-talkie, if you want to name it like that. But nowadays, our larger satellites, they communicate via full duplex. So you have, for example, an uplink on 2.2 gigahertz and downlink on 2.4 gigahertz. So while you are uplinking on the one frequency, you directly have your downlink on the other frequency. So you have simultaneous communication with the satellite.
So, for example, it would be like all three of us talking simultaneously, and everyone understands everything. Yeah.
Okay. That I think that you need some kind of machine to do that. Yeah. When you look into the future of SDR, what do you see? What's the next step?
Do you want to take that one?
Yes.
Let's ask the guy at the university. You should be the one answering this.
Well,
Andreas.
Let's say from the I will start with the educational part. It's for me as I use SDRs to educate people to understand what's actually happening on radio waves all around us. Everyone started to understand it more easily, because you can also, with the software-defined radio, you can visualize what is happening in different ways than using an old hardware spectrum analyzer. So basically, that's the first part. You can actually see, it's called waterfall diagrams. You can actually see what happens on air, on different frequencies all the time simultaneously. Instead of just tuning in onto one special radio show, for example, you optically see several radio shows next to each other. And for the future, it don't only raises the understanding of this technology, but also as we had the example of simultaneous communications next to each other. This will intensively rise on parallel communications that are at the same time talking, sending, receiving. So basically, it will get louder in the air.
And just to get that, why is that a good thing that you can suddenly receive more signals? Is that because it's machines more and more? It's machines talking to each other, so it's just the speed of communication is larger, or is it something else?
The amount of data transmitted per second will rise with this technology. It already did. And also, as we talked about, using one software-defined radio for several antennas, for example, gives also more versatility on the other end. So you can, for example, receive the same signal with anything. Speaking.
Maybe also here, what you can have, for example, 2 downlinks and 2 uplinks at the same time, also from the same satellite. Of course, it's 2 antennas, but that, for example, would be possible, and you can double the amount of data you can transfer of that. And so maybe also to get a little bit back to on the topic or from the ground stations point of view, or how we see the software-defined radio here in the future. I'm here always, or we at Terma, for example, also thinking here at ground station as a service. Since when we have our SDR in place, we have our Terma SDR model, for example, we can have a broad frequency range from, for example, 10 megahertz to 6 gigahertz with the various modulation schemes that are used as per the different standards. And that enables you, together with the virtualization, we already have talked about virtualization in testing application, but you can also have that for sure in the ground station. So you can book a ground station, let's say, as a service, and you use that virtualized or digitized signal, and then you have several, let's say, microservices available, because you have, for example, your modulator, your demodulator, deframer, or even decoding. There are various error correction schemes. If you receive a signal, there for sure will be errors within, and with that you can correct it. And so you, for example, can book these different microservices and directly get the data from the satellite, for example. So you don't have to build your own ground station. You can use another general purpose ground station via this virtual interface. And there's, for example, where I see one of the big roles of software-defined radio in the future.
Yeah, and that not only talks into, of course, the fact that some companies they may have it as a service that you can buy from them, but obviously it's also going to enable smaller companies, CubeSats. It's going to enable students to send stuff up without it costing millions and millions of dollars to establish a ground station.
Yes, it's.
And the university, you hooked up on that topic, when I remember correctly, because you also helping out the universities out. As far as I know.
It already started. We're not speaking about far future. It already started, and it is happening right now. So there's also a large open source community to not only enable individual persons, not only companies or educational institutes. So everyone can start with it right now and talk to many satellites with a very small budget. That more or less demystifies communication as it was within the past decades, because it was always a mystery. How does this work? Yeah? So now everyone can do it, look at it. Yeah? And for the virtualization point of view, for example, for our next mission, we cannot operate our ground station 24/7 with manpower. So we use this new technology to be able to access it from anywhere, anytime. If something happens, if we need to react to something, and that is also a benefit that comes with it for our team, for example.
So today we can actually, correct me if I'm wrong, you can actually log on to your satellite communication via a normal laptop.
Basically, yes.
That is pretty cool. I just saw the movie on one of the first Apollo missions. It's a completely different setup. Let's just say that. Yeah, it's like buildings upon buildings upon buildings with huge communication rooms and all this. It's just, and now it's just a laptop. It looks really cool, the other thing, but this is actually really cool, I think. Yeah. Okay, I think let those be the last words for this episode. Thank you so much for joining, Alexander Spaniol and Andreas Stren.
Thank you for the invitation.
Thank you so much.
You're welcome.
It was,
Thank you for this opportunity.
It was a real pleasure. The pleasure was absolutely on my side. And of course, to you guys out there listening, if you enjoyed this episode, do share it with your friends and colleagues or whoever you find or might find it interesting. And if you have any questions, reach out to us on podcast@terma.com. That was podcast@terma.com. And there'll be someone in the other end trying to, either answer your question or maybe take up that topic that you propose for the podcast and send it on to me. So that'll be much appreciated. I think that's all for me to say now. And the only thing left is to say thank you so much for listening.